Hi there, my name's Ewan. I'll be going over Lab 2 for Physics 2211, Motion of a Falling Object. So to start, our goal was to observe the motion of an object that falls somewhat slowly, straight down. I chose a crumpled piece of paper, captured a video of the motion, then analyzed the video in Checker. We were to construct a model based on Newton's second law that includes only the effect of gravity. We were also to construct a second model that includes both the effects of gravity and drag. Finally, we were to compare the models to the observed data by plotting position versus time on the same graph. Here you can see the equations for the forces involved in this lab. Weight equals negative mg j hat, and drag force equals negative b v squared j hat. To summarize the results of the experiment, the model that included both gravity and drag compared better to the observed data than the model that only included gravity, which overshot the final position relatively significantly. The model of drag predicts a terminal velocity as the slope of the velocity versus time graph began to even out as it become constant. So for the experiment itself, I recorded a video of one of my roommates dropping a piece of paper from around 180 centimeters above the ground. The mass of the paper is 4.5 grams. The initial velocity was 0 meters per second because the object is dropped from rest. The axis orientation, positive y, is pointing up, and the total time was 0.6 seconds. So for the initial conditions for the model, some things to note are that g is the acceleration due to gravity on Earth, that being 9.8 meters per second squared. J hat is the unit vector used in the weight and drag force equations. And the proportionality constant b is only used in the model of drag force. So for the calculation loop, you can see it executes for 0.6 seconds. I can see the coding equivalent of the weight and drag force equations, weight being the mass of the ball times g times j hat, drag force being the proportionality constant times the magnitude of velocity, which is speed squared times j hat, and the F net. In the case for the model which only includes gravity, F net is equal to W, and that's it. In the model where drag force and weight are both included, F net is as it's shown here, which is W plus FD. Changes in velocity and position, of course, need to be reflected. So for that, we use Newton's second law again, the velocity update formula shown here, and the position update formula shown here. Another thing we had to include were these arrows. They represent the magnitude of the force vectors involved. Some things to note: the blue arrow represents the drag force, this arrow here. The orange arrow represents the weight force, this arrow here. And if you notice, the blue arrow increases over time. Onto the graph itself, which has all the data on it. The drag plus gravity model, as seen, aligns pretty well with the experimental data. The gravity-only model overshoots the final position by quite a bit, relatively, which makes sense because in real life, gravity isn't the only force acting on the ball when it falls. Despite the fact that the drag and gravity model aligned much better with the experimental data than the gravity-only model, there were still some discrepancies as seen towards the end of the graph. These can be attributed to error. Manual tracking was not 100% accurate. The camera angle for the video wasn't perpendicular to the ground, so that was a bit off. The duration of the experiment itself was relatively short. It was like less than 20 frames. Moving on to the final questions. What does it mean? Examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? So the model accounting for drag and gravity does predict a terminal velocity. Terminal velocity being defined as what happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. What does this mean for the net force? Well, if they perfectly balance each other, that means the net force would be zero. They would have equal magnitude in opposite directions. And if the F net is zero, the velocity would be constant. And as you can see in the graph for the model, the velocity versus time graph, there's a gentle curve which indicates that the model is actually going to have the velocity flatten out eventually or become constant. So it would predict terminal velocity. For the what if, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Well, the terminal velocity would be the same. Plugging in an initial velocity that's not zero into the model, as you can see, the velocity versus time graph still ends up flattening out. Just the object starts at a greater velocity. Ultimately, this initial velocity is independent from the fact that the F net would eventually become zero from the drag force and the gravity force canceling out. And that is it. Thank you for watching.